Hi everyone! In this video we're going to cover the definitions of acids and bases. And while this is something you've probably heard before, a little review never hurts. So, an acid is a compound that contains an atom that is electron deficient. Okay? So how do we identify electron deficient atoms? Well, we look for polar bonds, and polar bonds will indicate to me where I have partial charge. Sometimes we will have a full-on formal charge, and we'll look at an example of that as well. So HCl is an acid you've probably heard of, hydrochloric acid. If we identify the polar bonds here, we can draw in the bond dipole arrow as such, and remember the sign with the little hash through it, it resembles a positive charge. That tells me where my partial positive charge is. The other side of that dipole will have a partial negative charge, and we use the Greek letter delta to indicate partial charges. So delta plus, delta minus. Okay, so if we're looking for an electron deficient part of this molecule, the hydrogen atom would be the acidic portion here. Now, if we look at something like the ammonium ion, NH4+, we can right away tell that this is electrophilic because it has a positive charge. The positive charge tells me that it's deficient of electrons. However, now would be a good time to remind you that formal charge does not always reflect actual charge. So thinking back to the bond dipoles, this is what's going to rule. Okay? Since nitrogen is more electronegative than hydrogen, right? It's closer to fluorine. It's going to bear the negative charge. Let me go ahead and make these arrows in a different color marker so that they are a bit easier to see here with everything being green. So we will have delta plus on these hydrogens and delta minus on the nitrogen. So in actuality, if we were to compute the charge using computational methods, we would find that the actual charge is different from the formal charge. And that's going to come up a few times. So when you're thinking about which specific atoms in a molecule are electrophilic, think about bond dipoles instead of simply looking for that formal charge. In chemistry, this theme of what you see is what you get does not hold true. Bases, on the other hand, are electron-rich. So, for example, a base that you're probably familiar with is hydroxide, OH-. Now, this will be paired up, of course, with a counterion, sodium hydroxide, potassium hydroxide, whatever. Okay, but we notice that this oxygen atom is electron-rich. It bears a formal negative charge, so that's quite obvious. This can function as a base and donate a pair of electrons to abstract a proton. Now, another example, let's look at ammonia. This is going to be similar in structure to the ammonium cation that we just looked at, but this is a neutral ammonia molecule. Now, NH3, this nitrogen atom has a lone pair. But if we think about the bond dipoles, we can see that this nitrogen is going to be electron-rich because it will bear a partial negative charge and have the electrons in the form of that pair to donate, right? This base has to be able to donate that pair of electrons, okay? And we'll look at some specific definitions of acids and bases in a second. Now I'd like to compare and contrast two different definitions that we'll use throughout the course for acids and bases. So the first is the Bronsted-Lowry definition, and the second is the Lewis definition. So the Bronsted-Lowry definition of an acid says that it is a proton donor. And a proton is an H, right? A hydrogen atom. Usually it'll be thought of as H+, right? Because it has to be able to accept an electron pair, and the only way to do that is if it has a positive charge. It doesn't have any electrons to start with. So, in order to be a proton donor, think about what structural requirement must there be for this to happen. All right? If it's going to donate a proton, it has to have protons, right? So, really, any molecule that has a proton, a hydrogen, can function as an acid, right? So, things like HCl that we looked at, carboxylic acids, right? There's two different hydrogens here, and we can talk about which of those is acidic. Even something like methane, the fuel that's used to heat our homes, the main component of natural gas, is never really thought of as an acid, but according to the definition, it can function as one. And we'll talk about the spectrum of acidity and see where molecules fall on this spectrum. Now let's consider the Bronsted-Lowry bases. So if an acid is a proton donor, then a base is going to be a proton acceptor. And I want you to think about what is going to be a structural requirement for a base to be a proton acceptor. It has to have electrons, okay? Must have electrons, right? A lot of times this will be as a lone pair, okay? And other times it could be something that has a pi bond, okay? So lone pairs and pi bonds are going to be the two types of bases that we're going to see. So examples of bases, hydroxide ion, of course that has excess lone pairs, and we can tell that right away with a negative charge. Ammonia, as we saw before, it has a lone pair of electrons. Water, similarly, has a lone pair. Interestingly, ammonia and water also have hydrogens, so they can fall under the acid definition as well as the base definition. So sometimes we'll see ammonia functioning as an acid, sometimes as a base. Same thing with water. Okay, so we'll tease out how we know whether it's going to be a base or an acid eventually here. And then something that has a pi bond, like an alkene or even an alkyne. So those types of functional groups can also serve as acids. These pi electrons can reach out and grab a proton. Okay? Now, let's compare the Bronsted-Lowry definitions to the Lewis definitions. All right? Under the Lewis definition, an acid is an electron acceptor. And this definition is much broader and allows us to encompass a wider range of compounds into the Lewis acid category compared to the Bronsted acid category, where we are talking about protons specifically, right? So it has to have protons. Here, electron acceptors, it just has to be able to accept electrons. So when we think about our traditional acids like HCl, if we have some base, right, with electrons, and this comes along and takes the proton, right, this hydrogen of the acid, HCl, hydrochloric acid, is accepting electrons, right, an electron acceptor. And this gives you BH plus the Cl minus ion. So acid is accepting a pair of electrons. And it's kind of misleading to say that it's accepting that pair. It's really accepting that pair. It's sharing that pair. Okay? Then we can say all of the Bronsted acids are going to be Lewis acids because they will react in the same manner. Other compounds that fall into the Lewis acid category are going to be carbocations. So carbon with just 6 electrons, it's electron deficient. So in order to be an electron acceptor, it has to be able to accept them either through an easy bond to break, right, because hydrogen can't have more than 2 electrons, or by having an empty orbital to accept electrons. So some base can donate electrons into the empty p orbital on the carbocation to give you the new bond. And depending on what B is, it may have a positive charge. If it's charged initially here, then it would be neutral. But this is the idea. So we form a new bond here. This carbon has accepted an electron pair. Okay? And similarly, carbonyl compounds, if we use our bond dipoles to determine partial charges, we'll notice that there's a partial positive charge on the carbonyl carbon here, making that electrophilic. And since the pi bond here is pretty easy to break, some base can come in and form a new bond with the carbon. Okay, so these are some examples of some Lewis acids reacting with bases. So, what does a Lewis base do then? All right, well, a Lewis base would be an electron donor. And electron donors will, as the name implies, donate a pair of electrons. Again, this is a little misleading. It's not giving up a pair of electrons. It's just sharing those electrons with another nuclide. So water is an example of a Lewis base. Again, structurally, if it's going to donate electrons, it has to have electrons. So must have electrons is also going to apply over here. Lone pairs or pi bonds. These same examples are going to fall into the Lewis base category as well. There's really not a family of compounds that I can think of off the top of my head right now that will be only a Lewis base and not a Bronsted base. Okay. Of course, some things are better Lewis bases, like bromide, Br minus, is a better Lewis base, or a nucleophile, right, if we want to use that language, compared to Br minus as a Bronsted base is very, very weak. So there will be differences in terms of the strength depending on how they are reacting, okay? So anyway, Bronsted-Lowry definition deals with the transfer of protons. Lewis acid-base definition deals with the electrons, whether it's accepting or donating. So if you have any questions, please reach out and get in touch with me. Thank you for watching.